All right, welcome everyone. I have to say, first of all, thank you very, very much for choosing to come, because you had the choice between sitting outside in the sun with a delicious cold beer or coming to sit here inside and listen to this talk for the next 50 minutes. So we're going to try to make it interesting. You've had a long day behind you already, so it's I know it's a lot of stuff to sink in. So we'll have a bit of a bit more fast-paced talk. Over the next 50 minutes, I'll have about 100 slides plus a demo, so it's going to be rock and roll, but that's good fun. So we're going to be talking about immutable infrastructure, which I think is one of the very fascinating developments we're seeing these days. And so we're going to dive into quite a bit of detail along the talk. We're going to look at the challenges, the implications, and everything around it. A little bit about myself. So my name's Axel Fontaine. I'm originally from Belgium, living in Germany these days. I'm the founder and CEO of a company called Devoxx. We specialize in deployment of JVM and Node.js-based applications on AWS with immutable infrastructure. So what you're getting today is a lot of the lessons learned and the principles we've based our things on. So hopefully there will be a few interesting bits of information there for you as well. I'm also the creator of an open source tool called Flyway, which you may know, for database migrations. Who's heard of Flyway before? All right, so about 3/4 of you. Excellent. So for those who haven't, it is a tool for evolving schemas in a relational database. So if you're doing that ad hoc, just make sure you use a tool to help you there. Any tool is better than no tool. So, as I said, it's going to be a pretty packed schedule, so if you have any questions, please hold on to them till the end. We'll have plenty of time afterwards. I'll do my best to answer them, and so if people want to move on after the talk, we're not holding them back either, but we'll have plenty of opportunity to answer all the questions at the end. So let's get started. And we're going to get started by taking our big time travel machine. And we're going to travel back to the wild times of the 20th century. We had these guys running around. This was how we used to play music, and this was how we would rewind it. So it was pretty wild indeed. And we had this guy. And he loved it when a plan came together. So when his plan was to get a server, this is how he would do it. He would get on the phone, the old style with the cords, and he would call his good friend Michael, and he would say, "Hey, Michael, I would love to get a server." And Michael says, "Well, no problem." And a few weeks later, a pizza box would arrive in the mail, and then you screw it in the rack and connect the network to power, and then what? Still doesn't work. So he gets back on the phone and calls a young criminal from the western coast of the United States that delivers him some criminal software, which then gets installed and patched and so on. So for the longest time, this was actually the workflow we had to go through. And if you look at this, we actually have three major components. We've got the data center itself, we've got our hardware, we've got some software. And if you have all that together, that's your classic on-prem story. And it's actually quite a difficult one to master. We have a quite important number of challenges that must be successfully mastered to be able to bring that to success. So there's mundane things like having reliable power and backup generators and all that stuff. There is having networking that's reliable, redundant, cooling and airflow of buildings. And then there's things like physical security of buildings that needs to be guaranteed, or things like having enough physical space, because it's not enough today if you have an existing system and you decide to upgrade the storage. Well, you can't just wheel the old storage out and wheel the new one in and reconnect everything. You need to have enough space to kind of have old and new at the same time. So these are all kinds of things that must be thought about. And once we've solved all those, we get onto the server hardware, where we have to deal with procurement and the whole relationship with Michael and planning capacity a long time in advance, as well as securing financing. And once we've done that, then finally we move over to the software side of things, where we install and patch our operating system, and we install and update our application. So when we actually have all that here, there's really a lot that must be taken care of. And at some point, some people started saying, well, you know what? Becoming experts in actually knowing how to run diesel generators is quite far removed from our core business. Or I don't really want to know how to build the best flooring to set my racks on. I just don't want to deal with that. So luckily, we've got a good tool ready to help us, the credit card. So some people said, well, you guys are really good at that. So can't you guys take care of this? I'll come with you and I'll pay you a certain amount. So we kind of get rid of the data center, we come with a credit card, and this is our classic co-location model, where you basically have your own servers within somebody else's data center, so they provide a 19-inch rack where you can then fit in your 1, 2, or 4U machines. You've got the power, you've got the network, and off you go. Now, all nice and well. But the whole relationship with Michael, kind of tedious, long lead times, all the financing and the planning that has to be taken care of, really not that much of our core business either, said quite a few people. So again, let's take the credit card and say, why don't you guys take care of that since you're really good at that, and let me just deal with the software. And this is really the classic root server model, which you have at Hetzner or OVH, where you've got excellent value. When you think about it, an i7 server with 64 gigs of RAM and half a terabyte of SSD costs about 50 euros a month at Hetzner. So it's really fantastic value. So this is our classic root server model. Now, let's focus on software. First of all, let's get to know each other a little bit to see where we all stand here in the room so we can see. So I would like you to raise your hands and keep your hands up as long as what is on the screen applies to you. So are you currently working on a project with an automated build? The gentleman in the front is not? Okay, fair enough. It's usually the question to check if everybody's awake, but no, fair enough. Okay, honest answer, appreciate it. Who's got unit tests on their project? Still pretty much all the hands? Excellent. Who's doing continuous integration? I see 1, 2 hands coming down, but not that many. Okay. Who's doing acceptance tests these days? And the kind of Selenium WebDriver type of? Very good. That's a very good number. We're at about 80, 85%. Who's doing continuous deployment of code? A lot of hands go down, but quite a few stay up. So we have about 25% of you still who also continuously deploys database and configuration changes. Few hands go down, still about 20% up, very good. And who does fully automated infrastructure deployments? We have about 20 hands left. Excellent. Okay, so if we look at the flow that we have there, where we've got our version control system on the one end, and we commit some change, then we've got our neutral referee, the CI system, that says, well, it's all nice and well that you committed something, but I'm going to double check whether you haven't introduced a dependency on your local machine, or whether you haven't forgotten to check something in. So I'm going to pull down the latest version of the sources, I'm going to compile them, I'm going to test them, and I'm going to produce some kind of artifact. The JVM, this artifact is usually a jar file, a WAR file, an EAR file, but could be an RPM, a zip, or anything else we choose. The artifact we produce has a number of qualities which we've learned to appreciate over the years. The first one is we produce one immutable unit. So when we produce our jar file, and if something needs to change, we don't really unzip it and change things and zip it back up again. No, instead we simply commit another change, which then runs through the same pipeline and generates a new artifact at the end. That artifact then gets promoted unchanged from environment to environment. Why? Because we want to avoid the classic mistake of building a separate artifact per environment, which pretty much means that you're running a different artifact in production than the one you tested in test. So we don't want that. Okay. When you look at our stack and the different layers we've got there, if we've got the hardware at the bottom, then we've got some operating system kernel on top of it to drive it. We've got some libraries. We've got the language runtime, in our case the JVM, with an app server embedded or not in our application. So this is really the stack we're talking about. And when you kind of look at that CI workflow, most of what we talked about is pretty much dealing only with these top 2 layers of our stack. And the question is, why? Is there something fundamentally different about the bits and bytes that those 2 layers are made of versus the bits and bytes of those lower layers? Why are we treating these things differently? I'm not so sure they're that different after all. Let's see. So if we keep our little workflow in mind, where we've produced our artifact, we've got our target system here, and we're pushing our artifact out to an artifact repository and pulling it down on the other side to update it, it's actually not too bad when we look at this. So deployment, not that bad in a world like this. Unfortunately, the world rarely looks like this. It looks more like that, where you have many machines in many different environments, and they all must be kept up to date. The problem is, of course, that any difference that you introduce between those machines at any layer is a potential source of trouble. In an ideal world, we want all our machines to be as identical as possible. The other thing that complicates our mission here is that things don't just stay in place. At some point, these machines need updating. We need to apply layers. We need to apply updates at all layers on all machines. So whose job is that? That's the system administrator. The system administrator is responsible for keeping all these machines updated and in sync with each other across multiple environments. Now let's go back a bit further in time and look at this quote from this gentleman here in the automobile industry from about 100 years ago. If I'd asked my customers what they wanted, they would have said, a faster horse. And guess what? This is exactly what we got in IT. Instead of the system administrator, we now have the automated system administrator, better known as the chefs and puppets of this world, where you're basically performing the same task as the system administrator, just a little bit faster, a little bit more reliable, a little bit less error-prone, but the basic task of aligning different machines with each other or with recipes or with templates is pretty much the same. There is no fundamental change involved there. So, let's take our time travel machine and travel back to the present day. This is a quote from AWS reInvent 2014, so it is more than 18 months ago already. This is from the big yearly Amazon Web Services conference in Las Vegas, and you really have to let it sink in to realize the magnitude of it. Every day, AWS adds enough server capacity to power the whole $7 billion enterprise Amazon.com was in 2004, weekends included. That's yesterday, that's today, that's tomorrow, and the day after, and again, and again, and again. It is just incredible. We have never experienced something like that before. We have really moved from a world of scarcity where we have to carefully look at which resources we have and really optimize for what we have to a world of abundance. And this opens up a whole new bunch of possibilities in how we design and slice and dice our systems. The other thing that's quite interesting that's been brought to the table there with the modern cloud is a clear separation between the control plane and the data plane. In this example here, we've got a nuclear power plant. The control plane is the control room where you've got all the dials and the knobs and where you can monitor everything. And the data plane is where you've got the pool with the submerged rods, which are actually where the reactions are happening. And so if we bring that back to software, the control plane would be your console, for example, and the data plane would be your actual instances performing work. Now, the new thing that's been brought to the table is that the control plane can be fully driven by machines. We've got APIs so that you can, in a fully automated fashion, provision a whole bunch of resources there. And something that's never been possible before, you can now turn them off and stop paying for them. This has never been possible on-prem, where basically hardware is a sunk cost. Whereas now, if you've got some monthly billing process that runs at the beginning of the month for 5 hours, you start it runs for 5 hours, you shut it off until the next month, and you stop paying for it. And this is really something which I think is one of the most fascinating developments we're experiencing right now, where we've got a conversion between business and architecture. It's still early days, we're still learning how to do that, but I think for the next 4 or 5 years, this is going to have a huge impact in how we slice and dice our systems. And so in light of that new reality, I strongly believe it is time to rethink the faster horse. If we start by assuming that what we have at the bottom there is just undifferentiated heavy lifting, and we rip out the physical hardware and replace it with virtual hardware, we now have a bunch of new possibilities that arise. Instead of producing just regular artifacts, we can now start producing images of entire machines, which we can then push to our artifact repository and pull down in one go onto our virtual hardware, so that we basically move from a world like this to a world like that. If our machine images are designed properly, they may even be able to run on multiple kinds of virtual hardware, and all the updates that we had to apply on individual machines, on individual layers, now vanish because they've already been baked in as part of the build process, so that the same machine image can then be deployed unchanged and promoted unchanged from environment to environment. But of course, there is one big problem left. When we look at the size of our machine images and the size of our network pipes, we've got a bit of a mismatch here. It is complicated, time-consuming to transfer these machine images over the internet. It is expensive to archive thousands of versions of them a year. So it's really far from ideal. So what can we do? Well, let's turn to some wisdom once again. This is a quote. I forgot who I've got it from, but it's a very good one. Running servers in production should be like going backpacking. You take the bare minimum with you. Anything else is going to hurt. Now, this is a picture my wife and I took 2 years ago. So yeah, I think pretty much this time of year, early summer in the Bavarian Alps. So it's Saturday morning, 10 in the morning. We're about to go for a hike in the mountains. So it's about, the hike we had planned was about 1,000 meters vertical. So proper hike. And we see these 4 guys coming down. And so they'd gone up the mountain the night before with a 20-liter wooden barrel of beer and the 4 big glasses and the hammer. And so they drank the whole barrel between the 4 of them at the top of the mountain and just came back down in the morning. So when you think about it, it is really the most inefficient way possible to get up that mountain. It's a bare minimum. Yes. But yet, when you look at how we run our service, this is exactly how we do it. We've got a 20 megabyte application and then gigabytes of stuff around it. It just doesn't make sense. And so, if we're going to be trimming some of that fat, we should decide which criteria to go by. I'm a strong believer in seeing our software industry as an enabler for the business, where we enable the business to move faster, more efficiently. And so I think it is quite important to look at that and see what is actually adding business value in those machine images versus what is just technical ceremony. So let's have a look. We have our machine image here. We're going to X-ray into it. We have a bunch of components available. In reality, there's more, but I put a few up here, and we're going to go down and see which ones are actually adding business value versus which other ones are just technical ceremony. So let's start. We're going to start at the top left, our application. That's what we're actually being paid to do. It's actually solving the problem, so we're going to keep that. But in a virtualized world, do I need compatibility with old binary formats or 32-bit CPU architectures? No. But I'm going to keep my app server embedded or not in my application to make the application run. But on my production machine, has a man page ever helped my customer? No. Has a customer ever been excited about the fact we were running RPM or apt-get on those machines? No. Goodbye, package manager. We're going to keep the language runtime because we need that to run our application. But if our application is written in Java, do I need a C compiler on those machines? No. It is not 2006 anymore. The days of having multiple terminals open with tail-F and grep expressions and watching logs scroll by is really something that belongs to the past. We have fantastic solutions available today with great centralized log service. You do not want to give access to individual production machines. You do not want to go hunt on individual machines to see where a request may have landed. So we do not want the log files up there. And if we don't have the log files, do we need a VI? Do we need the other editors? No, we don't. So many random Unix utilities that are lying around on those machines absolutely don't help our application either. So off they go. And if I haven't got any of that, do I even need to log in? I say no. Goodbye, SSH. If I can't log in, why do I need multiple users? If the very things I set out to protect simply aren't there anymore, why do I need a firewall? Do I need multiple shells? No. Do I need drivers for tens of thousands of pieces of hardware when all I need to support are 3 or 4 virtual interfaces? No. I'm going to keep some libraries to make the language runtime run and many random daemons we can dispose of, and we're going to keep the OS kernel for the hardware. And so what we have here is really the bare minimum, which is actually adding business value. And so when we fuse all that together, we get what we call a bootable app. And this is really a very different world. So for Node.js-based applications, for example, this is about 15 megs plus the size of your app. For Java 8-based applications, this is about 40 megs plus the size of your app. And that includes the Java runtime, all the libraries it needs, the kernel, and a bootloader. And so all of a sudden, when you look at that, it doesn't look that bad anymore, transferring one of those over the network or archiving thousands of versions of that per year. Not that big of an issue anymore. Now, I know that a number of you are thinking right now about a bunch of scenarios where this would never work. Well, it doesn't matter. Just use it for everything else. Because this is a perfect fit for the modern cloud-native microservice type of application. As much as we would all like to go back to the office next week and then think we're working on the next Google, on the next Twitter, on the next Facebook, the reality is very different. We are usually not pushing the boundaries of technology. We are just trying to get the job done. And so this is just part of industrializing and part of that infrastructure away so that we can really focus on what matters. So to show you that this is not just hot air, we're going to do a bit of a demo. So I've got a small Spring Boot application here, and we're going to run through that. So I'm going to use my company's tool there, BoxFuse, for that. So we've got our Spring Boot application here. I've got a simple REST controller. So I'm just going to modify it because it's of course never fun if it couldn't fail. So so those are the ways demos go. Let's save this guy. Just going to quickly rebuild it. Just going to rebuild the executable jar. Just a second. Should take 2 or 3 seconds. All right. Spring doing its thing. This is just a run-of-the-mill, very simple auto-generated application. Okay, so we've got our jar file here, and the first thing we're going to do is we're going to turn that executable jar file into a machine image, and we're going to run an instance of it on VirtualBox. So the first thing happening here is really a discovery process where we're kind of scanning. We found that we've got one matching artifact. That artifact is a Spring Boot executable jar that requires a JVM. A JVM requires a C library. A C library requires a Linux kernel. A Linux kernel requires a bootloader. And so we assembled all those pieces together. Just scrolling back up, and we got our machine image here. So total size about 55 megs, took about 5 seconds. We discovered that we had one port available, port 8080, that we need to map, our HTTP port, and then we launched an instance of it where we acquired the DHCP address and then pretty much here print the summary, and this is our Spring application booting, and it's up and running. So let's just grab the address. I'm going to take this guy here, and I'm going to paste it in the browser to see what we've got there. So up, open a new tab, there we go. And this is basically our new application on a brand new machine image that didn't exist 2 minutes ago that we've got up and running in the browser. So what have we got here? If we kind of look at the images we've got, this is our one image we've just generated right now based on our executable Jar file. It's based on Java 874, and it's a Spring Boot application, one port, HTTP on 80, and this is the size of our image. And if we look at what we've got running, we see that we've got one instance of that image running using a gig of RAM and 2 virtual CPUs. It's all configurable and at that URL. So what we can do now is take this image and run it unchanged in the cloud. So we can take the image that we've got here and switch the environment to AWS, our production environment. Now you have to know there's nothing pre-configured there or nothing there. So what we're doing here is we're pushing the image out. You can see I'm not on the Wi-Fi. Yeah? I'm on the wired connection. We're pushing the image out, and we're verifying it because it's encrypted and signed beforehand. So we're verifying it on the other end, and now we're ready to roll it out to AWS. So what's happening now is that we've got a conversion process kicking in where we're converting it to a format that's compatible with AWS. We're creating an AMI, an Amazon machine image. So when we created that image originally, we really created something out of 2 parts, a disk image itself and a descriptor. When we launched it on VirtualBox, we kept the disk image as is and converted the descriptor that contains metadata about the ports, about a few other things, to a VirtualBox compatible format. And this is the same we're doing here. So we're basically keeping the disk image as is and then converting the descriptor to an Amazon compatible format so that we can register the AMI there. So let's see how long they need today for this. So usually it's about between 30 and 60 seconds, depending on the load. So this is the data center in EU Central 1, which is the Frankfurt region. So let's see. OK, so they need just over a minute now. We've created a new elastic IP address. So that is an IP address that you can remap from one instance to another. We've created a new domain, and we've associated it with that IP address. We have created a security group based on the port information that we discovered before. So this is, you can think of it as some kind of external firewall in the software-defined network where we just allow access to that port 8080 that we discovered before. Then we launched the T2 Micro instance. This is a gigabyte of RAM and 1 virtual CPU. In Frankfurt, that took about 30 seconds. We create some alarm on CloudWatch in case the underlying hardware is a problem, that it gets automatically recovered onto different hardware, and we waited for our instance to boot and to return an HTTP 200 with our Spring Boot application up and running. So that we got, and now we're remapping our elastic IP and the domain associated with it to that new instance. So that should take a few more seconds. OK, there we go. So let's copy-paste this guy here and go to the browser, open a new window. And there we go. Our new machine that we created from scratch 2 minutes ago is now running on AWS in Frankfurt, unchanged, down to the last bit and byte compared to what we had running locally. OK, so let's modify something here. So let's just say hello again, and then save this guy. Quickly rebuild the jar file. Take a second. OK. And let's run this guy. Well, let's go straight to AWS. So we discovered that we had a checksum change in the artifact, so we generate a new image for it. That's done, so we're pushing it out now. And we're going to go through the same process again of registering an AMI and getting it up and running. So there is no base operating system involved here, or no base Linux distribution or something. This is really generated on the fly from scratch. This is a Windows machine in this case, but it works on Mac, on Linux, on anything else. So it just kind of generated in memory the operating system with only the pieces that our application needs. So none of that fat, only just the meat, only the stuff that is actually adding business value. Okay, so let's see how long they need for this AMI here. So they're probably scrambling in the data center, quickly copying USB sticks from one machine to another in Frankfurt. So they're under pressure. We can relax. It's all good. Let's see how long they need. Okay, so we've got our AMI. We're creating a new security group, and we're launching a new instance. So we're expanding our footprint. And we're not terminating anything yet. The old one is up and running. And we're launching a second one next to it. So let's see how long they need for that one. A few more seconds.
Waiting intensifies.
Pardon?
Waiting intensifies.
Yes. Well, it's the kind of thing my wife will never understand. How can you look so at a black and white window and all be hanging there? But no. Well, we can't share everything. Okay. So our instance has been launched. So the old one's still up and running, and we're waiting for the new one to boot. So we're basically pinging it every second, seeing if we get an HTTP 200 from our REST controller. And we just got that, so now we're ready to remap the IP address. So it's still the old one up and running, still the old one, still the old one, still the old one, still the old one at our domain, still the old one, still the old one, still the old one. Should come. It's the fun with demos. There we go. Bang. We're live with our new machine, and the old one's getting terminated now. Okay. Let's go back. So when you look at this, it is probably quite different from the way most of you are deploying your software today. And so this is a change that has quite a few profound implications. The first one is that we really have a strong shift in focus, where before individual instances used to be front and center. Right now it's really the service that matters. The service should be available with enough capacity, with enough performance, but individual instances really become something disposable. This is where we get to our famous saying, treat your servers like cattle instead of pets, so that we move away from the model where they're all cute and they receive a nice little name and we make them just perfect to a world of mass production, where if you need another 10 of the same, there we go. You need another 20 of those, no problem. And of course, it's not without a crude reality at the end, because at some point you may not need some of those machines anymore. So you really have to decouple yourself emotionally from them, because the sad truth is, once you don't need them anymore, this is how they end up. So it is pretty brutal, but that's okay. And I'll tell you why. We live in an industry where for the longest time we've been updating machines in place, and that era is finished. CRUD for servers is dead. We are deprecating the U. We are getting rid of it. We're still creating machines. We're still accessing them. We're still disposing of them. We're no longer updating them in place. And that's a good thing, because when you think about it, now in our industry, you've got we're people who pride ourselves that, look, I've got this Linux machine and I haven't rebooted it in 3 years. It's awesome. And well, unfortunately, maybe it's not that great, because the longer an instance has been up, the harder it becomes to recreate exactly. And the bad news is, it will fail eventually. Whether it's due to hardware or to software, there will come a point where you will need to recreate that instance, or you will need to set up a second one identical to the first. And so that high uptime that we saw as an asset is actually in most cases more of a liability. The other interesting thing is service discovery. How do I know where my stuff is if machines come and go, if they get different IP addresses, how do I know how to deal with that? So this is a very active space. When you look at service discovery, from the good old zookeepers to the consoles, to the Eureka solutions that are being pushed around there these days. So we've got a lot of activity in that space. But I actually think a lot of that, or actually most of them, is absolute overkill for the world of the cloud. They were designed in a different era, either for on-prem, or in the case of Eureka, for the time before you could have internal load balancers between service A and service B, so that you could only have internet-facing load balancers. So what can we do? If we look at our current understanding of a good service boundary, where we've got our individual instances all accessing basically some storage, some database which is private to the service, and where we don't do database-based integrations between the services anymore, just because this takes away all the valuable layers of abstraction, of validation that a proper API can provide you. So we want to have some API above and not expose the raw low-level storage that we've got behind it. And so if you look at this model, what I'm proposing here is, let's expand it a little bit. Let's expand our definition of a building block. Let's expand our definition for a service and its boundary with one more piece. And that piece is a stable entry point with an internal registry. In our little demo, that stable entry point was an elastic IP address. The internal registry was the IP address remembering which actual backend instance it was associated with at which time. And so when we sent the request in the browser, we didn't have to care which backend instances we were talking to. We only needed to remember the elastic IP address. If you have more than one instance, we can use an elastic load balancer on AWS, for example, so that we can then forward the traffic to the individual instances. And whether it's these 3 instances serving our traffic now or a different 5 instances 10 minutes from now, as a client to that service, it's not my problem. All I need to remember is the IP address of the load balancer or the way to access it, and that's it. Once I know that, the rest is taken care of there. And so this is very, very nice to push this out, because it makes it for a very easy to reason about overall system architecture, where you just have these high-level blocks working together. Now, what about security? That's another interesting one, because when you've kind of taken away all these bits and pieces, you could almost rephrase this question as, when was the last time your toaster got hacked? Because I strongly believe that all things being equal, and the more moving parts you have, the higher the likelihood that one of them will break. I strongly believe that complexity is the enemy of security, and so by removing as much of that as we can, we gain a significant advantage here. So the first thing that we have here is that we've reduced the attack surface to the smallest possible one we can actually have. The nice thing that we also have here is that our instances don't live very long anymore. And so if somebody, through some miracle, still manages to Trojanize them, that Trojan, if it had been on that first instance, would have already been disposed of together with the instance a minute later. So this is really a very interesting change. And I think what is also very interesting with a model like that is that we just make it much harder to penetrate further systems in the network. If you think about it, on a classic Unix machine, it's just insane. We are actually providing all the tools that one needs to further access all the other nodes, to further penetrate out of the box for an attacker to use. It's as if somebody would break into a house, and as you get through the front door, you get presented with the chainsaw and with the hammer and everything you need to break through the other doors. It's just insane. So getting rid of those things is actually a very good thing. Now, what about configuration? Because you may say, well, Axel, all nice and well, but the same image on every environment. I don't want to connect to my development database from production or vice versa, so how do you deal with these things? So I'm a strong believer in keeping things as simple as possible and only moving to the next more complicated solution when you've reached the limits of that. So I think what you should really look at is try to bake as much of that configuration for all environments directly into your image. This is something where you have a lot of configuration properties which are really uninteresting, which are only relevant for your app, and it's very, very easy to all place them in there. You can combine that with environment detection to find out automatically at runtime in which environment you're running, and so that you know which set of configuration to load. And for the remaining bits of configuration, if you have some sensitive passwords or some other things you want to pass in at instant launch time, we're in luck, because every single cloud provider today gives you the possibility to pass in arbitrary data on instance startup. On AWS, this is called the user data, and so you can use that arbitrary data for what you want, including passing in, for example, a shell script that does a number of exports for environment variables, which your application can then use. And so once you launch your instance, you've got all that available, and you can combine these different techniques to have a very effective solution. This, of course, does not prevent you from using configuration servers or other things either, if those are more suitable for your environment. Now, state and databases is also quite interesting, because if your instance is being disposed of, it also means that you do not want to store any persistent state exclusively on that instance. It's okay to cache some things there temporarily, but you should be prepared to lose everything that's on that instance. So how do you deal with it? We talk to an external database server. You can set up your own, or there are fantastic available services for that today. We, for example, have been using Amazon RDS Postgres for a few years, and it's been fantastic. With a single checkbox, you can have it geographically redundant and highly available. You have point-in-time backups. It's all these nice things are taken care of for you, but you can, of course, build your own as well. And if you have a relational database, you have to evolve the schema, so use a database migration tool on application startup to ensure that the database and the application always match. Again, here, use the simplest tool that could possibly work. I do not want to influence your choice as to which one this should be. Just pick the one that works for you. Now, it's not 2006 anymore, so the days of having individual log files on individual machines are over. We don't want our 5 little windows with tail-f expressions and all that, so we get rid of all that, and instead today we have a fantastic solution called the centralized log server, where you basically send the logs in real time, where they get processed, they get ingested, they get aggregated, they get indexed, stored. You can make them accessible. You can define alarms on them. A whole bunch of interesting things that you can do there. And again, you can build your own with Elasticsearch, Logstash, and Kibana. You can buy things like Splunk, or you can use hosted services like Logentries, Logly, or Papertrail, for example, that integrate very nicely with Logback and Log4j, for example, on the JVM side. Now, sessions is another interesting one. It's one where, as an industry, we've had a number of amazingly bad ideas over the years on how to deal with that. Certainly on the JVM side of things, where we first tried to have things on just a single machine. Well, we realized if that machine dies, that's not so great. So let's cluster it, let's see how that works, but once we get beyond a few machines, you start having a lot of chatter on. Let's see. Sorry, I need to do it once again. Okay. Oh, good. So once you get beyond a few machines, it's not a helium glass, I promise. Once you get beyond a few machines, you get a lot of chatter on the network, and that's not ideal either. So we tried shifting the complexity to the load balancer, where we then had sticky sessions and server affinity and draining the sessions. But unfortunately, that in the world of continuous delivery doesn't really work anymore, because if you're here in Poland and somebody comes into the office at 8 in the morning, that session can survive 8, 9, 10 hours. So that's much too long to be able to wait and kill these things off. So we have to come up with something else. And so a good solution here is what's actually been used on a number of other platforms for years. What Rails has been doing since Rails 2.0, what ASP.NET has been doing, what the Play framework has been doing from the beginning, is putting the session in the cookie. You can make it secure by signing the data and by encrypting it, so you make sure that it's not being tampered with and that it's not readable. And with that, you can avoid a whole bunch of things like session timeouts, because now you've outsourced your session storage to the client, so you basically can deal with an infinite amount of sessions on the server. You just need to provision enough memory for to deal with the requests that you are actively processing. So that's a very different number. You can get rid of all the complexity with clustering and session replication, sticky sessions. All of that we don't need anymore. Rolling out new versions, we've seen it in the demo. So if we've got our application up and running, we've got a load balancer to talk to it, send a request, send it to the database. The application in the cloud is running in a so-called availability zone. This is one or more data centers in a specific geographic location. So if you want to have that highly available, you'll deploy it across multiple availability zones. These are usually on different sides of a large city, where they will be in different flooding basins and basically isolated even at the natural disaster level from each other. Our logs in the log server, our session in the cookie. Version 2. We deploy it. We make sure it's working properly. If we're happy with it, we start sending traffic to it. We stop sending traffic to version 1, and we shut it off. And so what we've done here is we've expanded and contracted our infrastructure footprint. If I have 10 instances, 10 T2 micro instances, for example, of version 1, and I launch my version 2, I can start 10 additional instances of version 2. So I've got 20 instances at that point, and if that's working well, I shut off the original 10 from version 1. By doing that, I will have increased my total monthly bill by about 10 cents of a euro. So it is really, really interesting. We get to a very different world, something that certainly wasn't possible on-prem. Now let's talk about the elephant in the room. What about containers? What about OS-level virtualization? What about the Dockers of this world? How do they fit in a story like that? To be able to answer that question, one must take a step back and first understand how modern CPUs work. So for the past 10 years, since 2006, every CPU shipped on the market by Intel and AMD has had hardware support for virtualization. And this has brought two things to the table. It has brought isolation of individual guests on a host system from each other at the hardware level. And it has brought a performance penalty with it by making it basically a little bit less performant to run within these VMs because you need to enter and exit them. So every subsequent generation of CPUs has worked on reducing that performance penalty by optimizing existing instructions, by adding new instructions for optimized networking, for optimized I/O from within VMs, to be able to do that to the point where today they are within 2 to 5%. Xen and KVM are within 2 to 5% of native hardware, but there's still a gap. So on-prem, you've got, if you're in a virtual machine world, you've got the hardware, you've got some hypervisors, some image on top, bootable app or classic, it doesn't matter. And you've got the blue line there, which is really the isolation at the hardware level. If you contrast that to containers, on the other hand, you have the hardware, you have a base operating system, you have a container runtime, and then you've got some image running in there. And there, it's really the question of how homogeneous or heterogeneous your load is. Can everything run on the same version of the Linux kernel? Do you not depend on Windows or different operating systems? Do you not need things like live migration of VMs, for example, then containers are a fantastic choice because you don't need to pay that performance penalty. You don't live in a hostile environment. Your different applications are not going to try to actively Troyanize or sabotage each other. So that's an excellent choice there. If you have a more heterogeneous environment or have made existing investments, then maybe VMs are a good option too. So this is really, at the end of the day, all your responsibility anyway. If you bring that to the cloud, regardless of whether you use VMs or containers, the cloud provider always brings the hardware and a hypervisor. And then on top of that, you then have some image, a VM image, or then a base operating system, container runtime, and then some container image in there. So how should you choose here which one to use? If you look at what your cloud provider is bringing you, to the table as part of the money you pay them when you launch an instance there, you've got a machine image registry, or AMIs. We didn't have to run anything or set anything up. That's all taken care of for us. They will take care of scheduling instances on individual physical hosts, not our problem. They take care of that. They will deal with Michael and ensure that enough capacity is available ahead of time. They will have enough storage available, and they will take care of a good software-defined network as well. If you bring containers into the mix, you actually add a whole other layer of virtualization onto the existing one. And you have to solve the same problems again. So it means that now, instead of just managing machine images, you need to come up with a solution hosted or not for container images. The same for scheduling of containers, for planning the capacity of the cluster you're running in. So, and there are solutions available. It's still a problem that you need to manage. You need to deal with volumes, and the same for the networking. You need to come up with solutions for all of those. So you basically have to deal with a whole new layer of the same problem. So when does that make sense to take that on to your responsibility? Let's bring this back to economics and business. So these €5 here buys you about a month of T2 Nano. So that's one virtual CPU and half a gig of RAM. So it's actually more. It's about 40 days of it. So if you bring that down to an hour, it's about half a euro cent. And so this is really the smallest unit of granularity you can work with today if you're dealing with VMs. And so the question to ask is, can your organization's budget live with a granularity of half a euro cent per hour or not? Is that too expensive for you or not? If it is too expensive, then it may be worth the engineering effort to further subdivide that capacity and have all that extra layer there piled on top as well to make it worth it. But what you should really look for is to optimize for your total monthly bill and not for individual resource usage. And it doesn't matter if you have a machine where you have 300 megs of RAM that are unused. Who cares about that? What really matters is what you pay at the end of the month, and that is what you should optimize for. So if we summarize all that, we've taken the lessons that we've learned at the artifact level, where we produced one immutable unit that we regenerated after every change, and we promoted unchanged from environment to avoid a classic mistake of building a separate artifact per environment, and we've applied them to the remaining layers of our stack. To make it practical, you should aim for going for minimal images that can make that work. And I think one of the most fascinating developments that we're going to see in the next 5 years is really the conversion of business and architecture and having cost as a primary driver into how we design and slice and dice our systems. So if these ideas resonated with you, feel free to run and implement them. If you have a JVM or Node.js-based environment and you want to deploy those applications on the AWS, feel free to check out the work we're doing at BoxFuse as well. Otherwise, I would say this should have been my last slide, but I've got a different one for you. Thank you very much.